Section 5.2 talks about infinite series. What a series is the sum of the terms of a sequence. We have some of those that are finite, so you add from 1 all the way to k, and this symbol right here stands for the summation notation, or simply summing those up. Oh boy. So this is where you start, this is where you terminate. This is called a finite series because it terminates at k, versus we call this S sub k, the sum of the first k terms of a sequence. Now, you notice here, this is an infinite sum. It does start at 1, so you substitute 1 in, then you go 2, 3, but this does not terminate. We call that S sub infinity, and we call that, of course, an infinite series. Or simply a series. Now, I do want to remind you of an infinite geometric series. If you multiply by r, if you multiply by the same value to get the next term of a sequence, that's called geometric series. If you happen to deal with an infinite series that is geometric and you're adding from 1 to infinity, and this is the general term of a geometric series, and we're going to denote geometric by G, and every time we're talking about geometric, we're going to talk about R. If R is less than 1 in absolute value, indicating if R is between -1 and 1, not including either end, then this infinite sum would be the very first term on the list divided by 1 minus that R, which is the common ratio, and recall to find R, take any term on the sequence divided by the previous term. So if I was taking 1 plus a half plus a fourth plus an eighth plus 1 over 16, and the list goes on, the joke goes, an infinite amount of mathematicians walked into a bar, or an infinite amount of customers walked into a bar. The first ordered a beer, the second ordered half a beer, the third ordered 1/4 of a beer. The bartender got upset from all the crowd. He gave them 2 beers and told them to leave. This is a geometric sequence in which R is 1/2. This infinite series will equal the very first term divided by 1 minus R. That is 1 divided by minus 1/2. If you get a common denominator for all of those, you're looking at 2 over 2 minus 1, which is 2. And if you happen to have a lot of free time on your hand and you're bored on the weekend, well, guess what? Take a calculator, take 1 plus 1/4 plus 1/2, 1/4. If you add about 30 of those, you'll get about 1.9998 maybe. And the more you add, the more this becomes 1.99. You'll never reach 2 unless you reach infinity, which is never going to happen. And if your calculator gave you a 2, that means the calculator rounds to 8 decimal places. If you use a computer, that wouldn't work. So, using sigma notation, write the following expression as an infinite series. This is an infinite series. This is the series n equal 1 to infinity. And you really want to get used to this alternating business because it's going to come up in the next chapter, toward the end of this chapter and the next chapter heavy. I'll take, anytime I see a sequence that is alternating, I take -1 and raise it to the n power. Now, you might be off. You might be getting this term instead of this term. And how do you check? Just plug n equal 1 and see if the very first term is +1. If you substitute n by 1, you notice that that's the first term is -1. The second term, when you plug in 2, that's +1. So you're off in the order. All what you have to do is either make the power a +1, shift it 1 to the right or 1 to the left, and that does the trick. Now if you let n equal 1, Negative 1 to the 2 power will be 1. Negative 1 cubed will be 1. Negative 1 to the 4th, 5th, and so on and so forth. And if I wanted to write this as a series, so this is gonna use really what you used back in the days in college algebra or pre-calculus, depending which class you took. Arithmetic and geometric, those are infinite. They all have a sign. It seems they all have a 1. So that's fixed. The varying part is this is 1, this is 2, this is 3, this is 4. Well, 1, 2, 3, 4, that's arithmetic. A sub n is a sub 1 plus n minus 1 times d, or you could simply say n. That'll work if you could see it right away. If not, this formula will do the trick. 1 plus n minus 1. What are you adding every time? You're adding a 1. So that will be 1 plus n minus 1, which is n. So the fixed part you always copy down. The varying part you would always need to figure out. Most of the time it's arithmetic or geometric, and if not, well, it's identical to what you learned back in the days. Now we want to get used to this summation notation. So compute the first 4 partial sums. S sub 1 is simply a sub 1, which is in this case 1 over 1. Done deal. S sub 2 is a sub 1 plus a sub 2. That is 1 over 1 plus 1 over 2. That is 3 halves. S sub 3 is a sub 1 plus a sub 2. Oops, sorry, wrong key. Plus a sub 3. Well, instead of redoing those two, I'm already aware of what those are. Those are 3 halves. Plus a sub 3. A sub 3 is 1/3. All over 6, that is 9 plus 2, that is 11 over 6. So this sequence has 1, this sum, sorry, actually you don't need to list them out. S sub 4 is a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, but we just figured out that S sub 3, so basically is 11 over 6, and a sub 4, put a 4 in there, that's 1/4, and that will be all over 12. That's a 2, 22, and that is a 3. That's 25 over 12. And that's all there is to it. Here, this is again an alternating series. Alternating series is a series that switches from positive to negative. S sub 1 is a sub 1, and if you put 1 in there, you get a negative 1. S sub 2 is a sub 1 plus a sub 2, that's negative 1. When you put a 2 in there, negative 1 squared is 1, that's a 0. S sub 3 is, well, obviously it's a sub 1 plus a sub 2 plus a sub 3, or I could simply say that is S sub 2 plus a sub 3, that is 0 plus a sub 3, put a 3 in there, negative 1 to the 3rd power is negative 1, and that's negative 1. And S sub 4, obviously that's S sub 3 plus a sub 4, because that's a sub 1, a sub 2, a sub 3, which is S sub 3, and that was negative 1. When you put a 4 in there, negative 1 to the 4th power is 1, and that's a 0. All right. We would like to figure out whether this series converge or diverge. Well, we are aware that this is a geometric series, right? That is the series n equal 1 to infinity, and let's see how this plays. That is, I'm multiplying every time by e over pi, right? Remember, a sub n is a sub 1 times r to the n minus 1. So that is 1 n minus 1. There it is. You could check. Let n equal 1. You get e over pi to the 0 power. That's 1. When you put 2, 2 minus 1 is 1, and so on and so forth. So we say r equal e over pi, an absolute value that is less than 1, because this is 2.7 and this is 3.14. So this infinite series converge, and the sum equal all of that infinite sum is going to equal the very first term divided by 1 minus e. And if you want to clean that up, both of those are an acceptable answer on a test. So this converge. Here we say, look, the same deal happens. This is the series n equal 1 to infinity. In this case, a sub n is a sub 1 r to the n minus 1. To find r, take any term divided by the previous term. So the first term times negative. We're taking pi over 3 square root raised to the n minus 1 power. Well, in this case, r equal in absolute value negative the square root of pi over 3. But that is bigger than 1 because you're looking at 3.14 divided by 3. That's bigger than 1, right? So the square root of that is bigger than the square root of 1. If that's bigger than 1, we know that geometric series diverge. It only converge if absolute value is between negative 1 and 1, not including exclusive. If it's included, if it equals to 1, if r equal to 1 or negative 1, then the series diverge. So far that's what we know, and they're going to focus on geometric series for a bit more. They say, and notice the book always calls a instead of a sub 1. For a sub n as follows, write the sum using geometric series of this form, state whether the series converge or diverge. All right, well, they're telling me this is geometric series. I know that r equal any term divided by the previous term, and I'm aware that a sub n is a sub 1 r to the n minus 1. Well, let's see how that works. I'm looking at this sequence. This sequence state the first term of the sequence is 2. A sub n divided by say sub n plus 1 is 1 over 2. So if I cross multiply, this says a sub n plus 1 is twice a sub n. And I could list the terms, but they told me it's geometric. So all what I need is to find r, and I know how to find r. R is a sub n plus 1 divided by a sub n. So I have a geometric sequence in which the first term is a 2 and r equals 2 as well. You could check. The first term is a 2. The next term, multiply the previous by 2. Multiply that by 2. So the way this works, I know this is the series n equal 1 to infinity of, and let's see how that works. A sub n is the very first term times r raised to the n minus 1. You could write it like that. You're welcome to do that. What is r? R is 2. Here, let me write it down. But if you notice, these have the same base, and if you multiply terms of the same base, a to the n multiplied by a to the m is a to the n plus m. Since they both have the same base, you write a single base and you add the powers. 1 plus n minus 1 is 2 to the n. And if you write it like this, that's acceptable as well. And here we go again. The very first term on this sequence is 1 over 10. If I cross multiply, a sub n is if I cross multiply, I get negative 10 a sub n plus 1 equal a sub n, right? Or simply, if I take the reciprocal of this, that will be the reciprocal of that. A sub n plus 1 over c sub n, which is my definition of r, is negative 1 over 10. So this is the series n equal 1 to infinity of a sub n. A sub n again is the very first term times r raised to the n minus 1. The first term is 1 over 10. Negative 1 over 10 raised to the n minus 1. Now I could clean that up just a bit. And I could say that is negative 1 to the n minus 1 times 1 over 10 times 1 over 10 to the n minus 1. So that is negative 1 to the n minus 1. And when you multiply those with the same base, you add the powers, and there it is. Oh, I didn't check. Did it ask if it converts or diverge? Oh, it does say whether it converts or diverge. Okay, here, absolute value of r is bigger than 2, therefore it diverges. Here, we know that absolute value of r is absolute value of negative 1 over 10. That is 1 over 10. That's less than 1. Therefore, it converges, and I can even find the sum. This infinite series will equal the very first term divided by 1 minus r. You could leave it like that, or you could say, look, they all have the same denominator. That's 1 over, 10. It was not 10 minus 1. We change that to a plus because both of these are negative. 1 over 11. Which means if you add those infinite terms, you're going to end up with 1 over 11. Now we come to something that's extremely important, something we're going to use for the remainder of the chapter. If I take the series 1 plus x squared plus x cubed, this is geometric. R is, take any term divided by the previous term, you multiply it by x, and you multiply it by x, and you multiply it by x. R is x. This infinite sum equals the very first term divided by 1 minus r. That is 1 divided by 1 minus x. So I developed 1 plus x squared plus x cubed equals 1 over 1 minus x, or I have developed 1 over 1 minus x. That's how we're going to use it in this chapter. Now this section, the rest of the chapter, especially chapter 6, that's the series n equal 1 to infinity of x to the n, but it should be minus 1. We're going to have that start at 0, and that's where this comes in. So this is how it works. Anytime I'm able to get a 1, it must be a 1, and a 1 right there, and a minus. Whatever this is, I can put it in there, raise it to the n power, and come up with a power series representation, something we're going to use all throughout this course. A massive deal. So if I'm going to take 1 over 1 minus y, well, it matched. I'm going to write this as a series n equals 0 to infinity of y raised to the n power. And that's what they want us to develop. And now we're going to use that in multiple sections, not only in this section. So here, we're talking about trying to figure this out. We say, wait a minute, that doesn't look like it. I'm going to factor radical x out. That's going to be 1 over 1 minus x to the 3/2. And let me show you really quick, color-wise, if I could match. I need a 1 there. It must be a 1. That must be a 1 as well. And that must be minus. And this is what I'm going to substitute in. So this is going to be radical x. This right here is going to give me the series n equals 0 to infinity of x to the 3/2 raised to the n power. And now all what I have to do is use some algebra and clean this up. This is x to the 1/2, series n equals 0 to infinity, x to the 3n over 2. If you multiply those, you add the powers. That becomes x to the 3n over 2 plus 1/2, or simply, this is fine, there's nothing wrong with that. You could write that n equals 0 to infinity of x to the 3n plus 1 over 2. It doesn't really matter. I'm not sure how they write it in the back of the book, and it makes no difference to us. And here we are. Now, what's the deal? Well, you're going to figure that out on the long run. We could take any function or any relation and write it as a power series. Well, secant squared is 1 over cosine squared of x. We have a problem. We need it to be 1 minus. Well, we know this is 1 over 1 minus the sine squared of x. Hey, it matches. That's a 1. That's a 1. That's a minus. Oops, it didn't change colors. And once I get that, I'm going to take this right here and say this is the series n equals 0 to infinity of the sine squared of x raised to the n power, or simply, actually that's good enough, absolute value of sine squared of x is less than 1. Then this converge, always, all good. Now we're going to take a slightly different direction. Okay, now in this entire chapter and the next chapter, we're going to be figuring out whether series converge or diverge, and we're going to come up with 9 different tests to figure out whether series converge or diverge. But out of those 9 different tests, or out of all of these different series, there are only 2 series that we could find the sum of. And the first one we already talked about. Anytime they say find the sum, you check, is it geometric? If it's geometric, if the absolute value of r is less than 1, then the sum is right there. If it's not, you're going to try and use this theorem, and this theorem works on telescoping specifically. So, this is an infinite sum. It talks about a series, an infinite series is an expression of the form 1 all the way to infinity. We call that S sub 8, S sub infinity. And this is what it says. Given an infinite series, we're going to be dealing with infinite series all throughout this chapter and the next chapter. If they're asking you to find the sum, then guess what? You're going to take some positive number k and take a portion of that. You're going to take S sub k terms of that infinite sum. So you're looking at the infinite sum, you're going to take a portion of it. This S sub k is called the kth partial sum of the infinite series, no big deal. The partial sum, we treat it like a sequence, S sub k. If this sequence of partial sum converge to some number s, then the infinite series converge, and we say, guess what? The infinite series converge to this same value s. Remember the deal for a sequence. So I'm given this infinite sum. Out of that infinite sum, I take a portion, S sub k. I treat S sub k like I would a sequence. I take the limit of this sequence. If that limit exists as a finite number, I say the infinite sum converge, and it'll approach the same value as that limit. A bit confusing, but let's see how that works. This is an infinite sum. Now, evaluate the following telescoping series or state it diverges. Evaluate means find this infinite sum. Now, let me show you what's going to happen. Anytime this happens, you list few terms. Let n equal 1. 1 over 1 to the 13 minus 1 over 2 to the 13. That's the first term. Next term, let n equal 2. Let n equal 3. Right? N equal 1. 1 plus 1 is 2, 3. Maybe one more just because that's the first one. N equal 4. And this is... Now, the last term on the sequence will be 1 over. So we're going to take S sub k. We're going to stop at k. The last term will be k plus 1 to the 13 and 1 over k to the 13. The term before will be 1 over k to the 13, 1 over k minus 1 to the 13, and maybe one more. 1 over k minus 1 to the 13, and that will be 1 over k minus 2 to the 13. Now watch what happens. Those two are exactly the same, but they're opposite. This is negative, this is positive. But those two are exactly the same. Once you cancel terms, once you see terms that are canceled completely, no need to go on because they're going to cancel out. Look at the last few terms. Wouldn't these two cancel out? And wouldn't these two cancel out? And again, once you cancel a whole term, everything in between is going to cancel out. So in general, this S sub k is going to look like the very first term minus the very last term. According to the theorem, you treat this like a sequence. You take the limit as k approaches infinity of S sub k. That's the limit as k approaches infinity of 1 over 1 minus 1 over k plus 1 to the 13th power. Now, as n approaches infinity, isn't that 0 and you end up with 1? You say, therefore, it converge, and the series n equal 1 to infinity of 1 over n to the 13 minus 1 over n plus 1 to the 13 equals whatever you get there. That's your conclusion. One more time. This theorem states, given an infinite sum, take k terms out of that. Call that S sub k. Treat that like a sequence. If this sequence converges to a number s, then we say the infinite series converge to that number s. Otherwise, we say the series diverge. Here's another one. Again, telescoping terms cancel out all the time. So anytime they say evaluate an infinite series, it's either geometric or you're going to use telescoping. Those are the only two we're going to use. Well, if I use n equal 1, that's sine of 1 minus sine of 2. N equal 2, sine of 2 minus sine of 3. N equal 3, sine of 3 minus sine of 4. And maybe one more just because, again, you're new to this. Sine of 4 minus sine of 5. The list goes on. The very last term, again, we're going to take k terms out of those. So instead of here, we're going to stop at k. So the last term will be s sine of k plus 1 minus and sine of k. The term before that will be the sine of k and the sine of k minus 1. And the term before that would be sine of k minus 1. And sine of k minus 2. Well, what do you notice? Those are exact opposites. Once you cancel a whole term, you know everything in between is going to be canceled out. And if you look at the last, those two are opposites. Those two are opposites, so this is going to cancel with the one before it. So this s sub k happened to be the sine of 1 minus the sine of k plus 1. And remember, we're going to treat that like a sequence. So we take the limit as k approaches infinity of s sub k. That is the limit as k approaches infinity of the sine of 1 minus the sine of k plus 1. But we know this has an issue. This does not exist because of oscillation. Therefore, this sum diverge. And that's pretty much it for this section.